So today I'm going to be going through all the steps I went through to complete homework 1. And to start, so we create a project in Quartus Prime with this device right here. And the first step is to create a new block design file or a schematic. So it'll pop up with this window right here, and what you can do is you can select this block diagram schematic file and you hit OK. And then once you hit OK, it'll come up with this little grid right here, and you can double click and you'll be able to select whatever you need. So under primitives, you can find the logic cells, such as the AND 2s that we'll need, OR 2s that we'll need, and the XORs that we'll need. And you can just hit OK, and then you can place one of these. If you need multiple, you can just hit Control C and then Control V to place another one. And then you can connect between them by holding your mouse cursor and dragging between the different nodes. And also what we'll need are input and output pins. So under the pin folder, you'll find input and output pins. And so for an input, we'd select that, and then you can change the name by double clicking here, and you could type in input 1 or something like that, and then connect it to your design. Now you can see that this full adder BDF file contains the design, which has 3 inputs, A, B, and carry in, 2 outputs, which are S and carry out, and that is consisted of 2 XOR gates, 2 AND gates, and 1 OR gate. So after we have this block design, what we're going to do is we're going to set it as the top entity, and then you're going to start compilation. You can just select this and hit start, right click it and hit start, and I will come back when this is finished. So now that compilation is done, the report has generated. And so we'll look at the fitter summary report. And what we'll see is that it is using 2 ALMs, 5 pins, and no other resources. And so the next step is to create the HDL wrapper for this design. So what you do is you go to File, you select Create and Update, and then here you would select Create HDL Design File from Current File. But since I've already done this, it is no longer an option, so let me add that to the project. Go here, hit Add Remove Files, and then here you'll see the little pop-up, and you can add the full adder.v, which is the Verilog file that this generated, and the file should look like this. And now that this file is added, what you will actually do is you remove the block design file. And now with this design, what we will do is we'll set this as the top entity file, and we will recompile. Okay, so now that the compilation is done, and we can see that the design still works, we will generate a test bench. What you do is you go to Processing, and then under this, you select Start. Select at basically the very bottom, there's a Start Test Bench Template Writer. And you would select this, and so you're going to rename the file. And I will show you how you rename it. It should get generated under the Simulation Questa folder, and then you'll see something like fulladder.vt, and then you'll rename it something like this. And now I'm gonna open this, and it's been modified already. Most of this is already generated by the tool itself. So how I have modified this is I've changed the A, B, and C to wires. I added a register called test vector. I created an integer so that I can use a for loop. Then I assigned A, B, and C in to the different bits of the test vector. I instance whatever full adder I want to use. So right now we're going to look at the full adder that we just generated. What I did is in this initial block, I assigned the test vector to 0, hold it for, it should be 1 nanosecond. And then I create a for loop that will increment the test vector 7 times and hold it for 1 nanosecond. Once you have your Questa properly set up, you'll select under tools, you'll select run simulation and then RTL simulation, and Questa will launch. Okay, so under the work and RTL work files, you can see the full adder file. So what we need to do is we need to go to compile and hit compile. And then in the file selector, you'll go to the test bench file and you'll select that. And you will hit compile and then done. And you can see that this full adder Verilog test has generated. And you right click on that and hit simulate. And now here you can see all the different wires and registers within the design. And I will select the inputs and outputs, and I will add that to the waveform. And then up here, you can see 100 picoseconds. I'm going to change that to 1000 picoseconds. So I've ran it 3 times. I need to run it a few more times until it stops changing. And then I'm going to zoom full. So up here you can see the inputs and down here are the outputs. So when all 3 inputs are 0, you can see that there are no outputs. When one input is high, such as right here, and over here, you can see that the carry out bit is low and the sum is high. When there are 2 bits high, like right here, and right here and here, you can see that the carryout bit is high and the sum bit is low. And then in the case where there is 3 bits high, there is a carryout bit and a sum bit that are both set to high. So this full adder is working properly. So now that we've verified that the schematic we built works, what we're going to do is we're going to make a full adder using RTL. So you'll hit the new and you'll create a Verilog or VHDL file. I'm just going to add my files that I already created back. So the full adder RTL file looks like this. Basically, the module is declared, the inputs are declared, and then the outputs are declared. Now, this is a very basic design. Basically, what I do is I concatenate C out and S, which is the sum, and set that equal to A plus B plus carry in. And so how I'm going to test this is I'm going to go to the test bench file, and I'm just going to change the full adder to full adder underscore RTL. I'm just going to set this as the top module, the top entity, and I'm going to compile that, and I'll get back with you after it is done compiling. So now that the design has compiled, you can see that there are no coding issues that will actually prevent it from compiling, and you can see that it is using 2 ALMs and 5 pins just as the other design. So now that Questa has opened, under work you can see the full adder RTL is there. We'll go to compile, hit compile, and then do the full adder test bench again. And what you should see is that it'll be exactly like the other one. And so what you can see is that that behavioral design, which is very small code, does the exact same thing as the schematic and the structural Verilog that it generated. And now if you wanted to actually see the critical path in this design, I'll just show you in this design. You will go to the timing analyzer. It'll pop up like this. And then what you can do is you can go down here and report datasheet. So here you can see this table, and basically what you need to do is you need to look out for the biggest number, which happens to be right here. So with the 6.64 nanoseconds, you can get 150.6 megahertz. So the next step in this homework is to create some 4-bit adders. And so for the structural design, what I just did is I instanced the 4 structural full adders into the design with a 3-wire array to send over the carry signals between the different full adders. And so under fitter, we'll look at the summary, and you can see that it uses 4 ALMs. It uses 14 pins. I kind of want to look at the post fitting here. And here you can see the design. You can see the different input and output pins. You can see the full adders instanced and some IO buffers. For the behavioral code, basically I just declare the module. I declare the ports, the input and output ports. And then I do the same thing as with the full adder, just with more bits. And what you can see here is that the design actually only uses 3 ALMs, as well as the 14 pins. And this design netlist is quite, and what you can see here is that instead of a regular full adder right here, it does something different. And this only happens because we're using the behavioral code and not the structural code. What you can see here in the datasheet is you get a much bigger spreadsheet. So what I like to do is I'll actually copy this and then I'll launch Excel. Just paste it in here, and then what you can do is this conditional formatting, and you can kind of set the scale. And what you can actually see right here is that this is the critical path. Then you can look back at the chart right here. You'll know that from A0 to S2 is the critical path. So as you can see here, I just kind of wrote a very small test bench right here. So I'm just going to use I'm going to start with the BHV, the behavioral model. And I'm just going to run this and make sure that it is properly functioning with only a few test cases. Basically all zeros, and then all ones, and then all set to the max. Kind of see what that does. What you can see here is that when the inputs are 0, outputs are 0. When the inputs are all 1, the output is 3 with no carryout, which makes sense. So when it's trying to add 15 and 15 with a carry-in, what you get is a carryout and 15, which is correct. So with that, we can kind of get an idea that this full adder is working properly. And so I want to do the same thing real quick, just with the structural model. Add the signals, get a divider, add the output signals, and then we'll run this for 3000 picoseconds. Zoom out, and especially if I change the radix to unsigned, that this full adder works exactly the same as the other one, or the 4-bit adder. So I think we can say that the designs work properly and they are equivalent. So that about wraps it up for this homework number 1. Thank you for watching.